Okay, so what we discussed today, went through it super fast. What we're doing is we're coding. We're transducing exercise from this frequency, intensity, and duration that we know that we have to systematically and progressively increase. The idea is that the frequency, intensity, and duration should be targeting specific molecules, because those specific molecules could then transduce the high intensity into a signal that's going to cause an improvement in function. The signal of a long duration is going to be able to transduce that long duration activity into something that's going to give us the adaptation we're looking for, which is more mitochondria, more blood vessels, and more fatty acid oxidation enzymes. All right, so what we talked about today was the fact that high intensity exercise, mostly through this AMP activation, through using energy faster than we're producing it, so that now we're having to drive ATP production instead of through glycolysis or through oxidative sources. Now what we're doing is we're having to use this myokinase reaction more to fill in the gaps between stored energy and glycolysis, to fill in the gaps between glycolysis and oxidative energy production. Because that's what this myokinase reaction does. It fills the gaps. It is giving us the bit that we're exercising higher at a higher intensity than we can produce ATP. So we need to produce the ATP through this side reaction, through this myokinase reaction, which is going to generate AMP. That's going to activate AMP kinase about threefold. It's going to get phosphorylated. That's going to activate another twofold. And then we're going to get downstream signals, which are going to lead to endurance adaptations. There's other signals as well. We talked about this NAD signal. It comes in part from pyruvate being converted into lactate to regenerate NAD, but it's also coming from exercise. As we're going through it, both in glycolysis, in the production of lactate, but also in the TCA cycle, we're regenerating NAD+, and that NAD+ is going to increase during exercise, whether you're young or old, and that NAD+ is going to activate sirtuin. And specifically, we talked about sirtuin-1. Sirtuin-1, when we increase its activity, we get a partial mitochondrial biogenesis. So we get a lot of the things that we see with endurance exercise. With AMP kinase, we get all the things we see with endurance exercise. So these two things together are going to give us endurance adaptations. So that's how we code for kind of high intensity is mostly the AMP kinase, a little bit of sirtuin-1. The long duration now is going to be coming through a different coding system. And instead of using an AMP code, what we're going to use is we're going to use a calcium code. And that calcium is going to activate the CAM kinases. The CAM kinase in muscle is going to be CAM kinase 2. That's going to work as an oligohexamer. And as an oligohexamer, it's now going to have this increased kinase activity. And it's a serine-threonine kinase, just like AMP kinase. And because it's also a serine-threonine kinase, and it does the same things as AMP kinase, what you should be thinking by this time is the two things might have the same targets downstream. And the same targets that are going to help you increase mitochondrial mass, blood vessels, and fatty acid oxidation enzymes. And that's really where we're going to go as to how AMP kinase and CAM kinase can now regulate the production of the endurance phenotype in the peripheral tissues.